Welcome to today's deep dive. Wow, you really went all out gathering material on Poisson numbers and sequences, encyclopedia entries, Wikipedia, research excerpts, even a study guide.
It really is fascinating how Poisson numbers pop up everywhere.
It is, right. So today,
Different areas of math, yeah.
we're going to try to figure out exactly what they are and why their properties are so interesting
Sounds good.
for someone like you listening who's interested in this topic.
Well, I think the best place to start is by defining exactly what a Poisson number is.
Okay.
So imagine like a very exclusive club with numbers want to get into.
All right.
But to get in, you have to pass this conjugate test.
This is a special club.
It is a special club, yeah.
Okay.
And that's the essence of a Poisson number.
Right.
It's a real algebraic integer greater than 1.
Okay.
And all of its Galois conjugates have an absolute value less than 1.
Okay, hold on. Back up a second.
Sure.
What are Galois conjugates?
Oh.
I've heard of the golden ratio.
Yeah.
I know that's a Poisson number.
Right.
But so explain those two things.
Galois conjugates, think of them as like shadow numbers that are associated with each algebraic integer.
Okay.
They provide us with information about the properties and relationships of that number.
Gotcha.
So, for example, the golden ratio, which is approximately 1.618, is a classic example of a Poisson number.
Okay.
Its conjugate is approximately minus 0.618, which has an absolute value less than 1.
So that conjugate passes the test to get into the club.
Exactly.
Okay, so it's not just any number.
Right.
That can be a Poisson number.
Correct.
It has to have that.
It has to have that special relationship.
Relationship with its shadow.
Yes.
Okay.
The Galois conjugate.
Now, you also mentioned that Poisson numbers are known for being almost integers.
That's right.
What's that all about?
So this is where things get really interesting. The powers of a Poisson number get very, very close to whole numbers, to integers.
Okay.
And this all comes from the relationship between an algebraic integer, its conjugates, and their powers.
All right. Break that down for me.
Okay.
Because that sounds a little complicated.
Yeah.
For someone who maybe hasn't studied a ton of math.
Let's start with the idea of an algebraic integer.
Okay.
These are numbers that can be solutions to equations that have integer coefficients. And if you were to take the nth power of an algebraic integer and all of its conjugates and add them all up, you'll always get an integer.
All right.
But because the conjugates of a Poisson number are less than 1 in absolute value, as you raise them to higher and higher powers, those powers are going to shrink very rapidly.
Gotcha.
Which leaves the Poisson number's power as like the dominant term in the sum and pushes that sum very close to a whole number.
So the Poisson number is basically taking over.
Exactly.
Pushing everybody else out of the way.
That's a great way to put it.
Right.
It's almost like they're trying to disguise themselves as integers.
Like a mathematical magic trick.
Exactly.
So why should we care about this almost integer
That's a good question.
behavior? Does this have any real-world implications?
There are a number of implications. For example, if you need very accurate approximations for complicated calculations, Poisson numbers are very useful in fields like physics and computer science.
Okay, so like for real-world
applications,
they're very important.
Precise.
They're kind of like the unsung heroes of precision.
Also help mathematicians explore the idea of something called Diophantine approximation.
Diophantine.
Yeah, which is just the study of like how closely you can approximate irrational numbers using rational numbers.
Okay, cool.
So they're almost like little secret agents, giving us clues about the connections between these different types of numbers.
That's fascinating.
Yeah.
I like that.
It's a very rich area of study.
Now, you mentioned Poisson sequences.
Yes.
And my notes here talk about a special recurrence relation.
Right. What does that mean?
Poisson sequences, much like the numbers themselves, have this very unique way of being generated.
Okay.
So they're defined by this very specific formula that involves what's called the nearest integer function.
Okay.
Which essentially just rounds a number to the closest whole number.
Gotcha.
And by applying this formula repeatedly, you can generate this sequence of numbers.
So we've got these sequences that are kind of bouncing around. Sometimes they're predictable, sometimes they're not.
Exactly. And that's actually a really good point.
Is there a way to tell like what kind of sequence we're dealing with?
There is some Piso sequences follow a very predictable pattern called a linear recurrence relation.
Oh, and these are called recurrent E-sequences.
E-sequences.
Yeah, and the values that you use in these recurrence relations for these special sequences are called E-numbers.
Oh.
And guess what? That these E-numbers can actually be Piso numbers themselves.
Oh. So we've got these sequences, they're kind of bouncing around, doing their thing.
Yes.
And the values that are guiding their moves can be these special Piso numbers.
Exactly. It highlights the connection between these two concepts.
That's pretty cool.
It is, yeah.
So can you give us a specific example of a Piso sequence?
Yeah. Let's look at the sequence. E7, 49 meters plus 15, where dem is any integer greater than or equal to 1.
Okay.
So in this notation, 7 and 49 meters plus 15 are the first two terms of the sequence.
Right.
And all subsequent terms are generated using that nearest integer formula.
Gotcha. So we've got this specific sequence.
Yeah.
It's rooted in this world of Piso numbers.
Exactly.
And it might or might not follow that predictable pattern, like a linear recurrence relation.
Right. And that's what makes it so interesting.
It's kind of like a choose-your-own-adventure story.
Exactly.
In number theory.
That's a great way to put it.
Okay, cool.
So we've got these E numbers, and we put them into different sets.
Okay.
We've got sets E, H, S, and T.
E, H, S, and T.
Okay, set E includes all E numbers.
Okay.
H is a subset of E where the distance between multiples of that E number and the nearest integer decreases very rapidly.
Right.
Set S, our exclusive Piso number club.
Yep.
And then set T contains what are called Salem numbers.
Okay.
Which are very closely related to Piso numbers as well.
Oh, interesting.
Yeah.
So it's like a whole, like a family reunion.
Yeah, exactly.
For all these different special types of numbers.
Precisely.
All right, now speaking of exciting.
Yeah.
Let's dive into the enigmatic set S.
Okay.
The exclusive club.
Yes.
For all Piso numbers.
That's right.
What makes this set so special?
So set S has some remarkable properties. One is that it's a closed set.
Closed set. What does that mean?
It means if you have a sequence of Piso numbers that's converging to a certain value, that limiting value has to also be a Piso number.
So they let you in.
They let you in.
If you can get close enough.
Exactly. It's like the club has this very strict membership policy, but those who can get infinitely close, they're eventually let in.
Right.
And another interesting thing about set S, a famous mathematician, Carl Siegel, determined that the smallest member of this set is a number called the plastic constant, which is about 1.3247.
Okay.
And even more interesting,
yeah,
the golden ratio, our star Piso number, is not just any member of set S.
Okay.
It's actually the smallest limit point.
It's showing off.
Of the entire set.
The golden ratio, it's like, I'm not just going to be in the club.
Right.
I'm going to be the bouncer.
Exactly. Yeah. And that was proven by Dufresnoy and Piso.
Okay.
So that really solidifies the golden ratios.
Importance.
This plastic constant.
Yes.
It sounds pretty interesting.
It is.
It's not as well known as the golden ratio.
Right.
But it's clearly got some clout in set S.
It does.
Okay, so tell me more.
The plastic constant is defined as the real solution to the cubic equation. Xi go by 1 equals 0.
Okay.
And one of the most interesting things about the plastic constant is its connection to architecture.
Architecture. Math and architecture.
It's true.
Okay, we're going to have to...
We'll delve into that.
Dive into that. That's fascinating. A connection between math and architecture.
Yeah. So this plastic constant, it's defined as the real solution to a cubic equation.
That's right. The equation is xi by 1 equals 0.
Okay.
And the plastic constant, which is approximately 1.3247, is the only real number that solves that equation.
Right.
But what makes it even more interesting is that it has a special kinship with the golden ratio.
Oh.
They're like family.
Okay, I knew there had to be more to this story.
Yeah.
Tell me about this family connection.
So both the plastic constant and the golden ratio belong to a special group of numbers called morphic numbers.
Morphic numbers?
Yes, and these are real numbers greater than 1 that can be expressed in two very specific ways using positive integers.
Okay, can you give me an example?
Sure. So for the golden ratio, these expressions are plus 1 x bis hos and 1 o is 1, 1.
Okay.
The plastic constant also has its own expressions, which are plus 1 o and 1 equals pro o.
So they both got these kind of hidden relationships, like
Yeah.
they're leading double lives.
That's a great way to think about it.
So back to architecture.
Yes.
How does this all connect?
So one of the defining features of the plastic constant is its connection to something called the van der Laan sequence.
Van der Laan sequence.
Yes, which plays a very important role in architectural design.
Okay.
So there was a Dutch architect named Dom Hans van der Laan,
Okay.
and he used this sequence to create harmonious proportions in his buildings.
So is this like a
That's a good question.
known thing?
So it seems like...
Like, did mathematicians discover that the plastic constant had this connection to architecture, or was it something that he intentionally
Yeah.
built in?
It seems like van der Laan was really interested in the aesthetics
Okay.
and the philosophical aspects of proportion.
Okay.
And he believed that certain ratios, like the plastic constant,
Mm.
held a special significance in human perception.
Okay.
So he very deliberately chose to use this in his designs.
Wow, that's really fascinating.
It is.
So how does this van der Laan sequence actually work?
So the van der Laan sequence is defined by something called a third-order recurrence relation.
Third order. Is there something to that?
Absolutely. So you have the plastic constant,
Yeah.
which is a cubic number,
Mm-hmm.
and then you have this van der Laan sequence, which is based on a third-order recurrence relation.
Right.
And as the terms in the van der Laan sequence get larger and larger,
Okay.
the ratio between consecutive terms gets closer and closer to the plastic constant.
So the plastic constant's like a magnet,
Yes.
pulling those numbers
Pulling them in?
closer.
Precisely.
That's so cool.
It's a really neat connection.
It is. It's amazing to me that he actually like used this
I know.
in his designs
Yeah.
and like created a sense of harmony and balance.
Right. The sequence itself starts with 1, 0, 1, 1, 1, 2, 2, 3,
Okay.
and so on. And as you go further and further along in that sequence, you'll find that the ratios between the successive numbers get closer and closer to 1.3247.
Okay, so before we get too lost
Yeah.
in the beauty of plastic architecture,
Okay.
let's shift gears and revisit that Piso-Vijar-Yargovann problem that we talked about earlier.
Right.
I'm really curious about this
Okay.
mathematical mystery.
So it's a problem that's really intrigued mathematicians
Okay.
for decades.
Right.
And remember how we talked about Piso numbers
Yeah.
and how their powers get so close to being integers?
Right. Right.
Well, the Piso-Vijar-Yargovann problem asks us to look beyond Piso numbers.
Okay.
And it says, are there other numbers out there
Yeah.
that have this same property
So are we?
where their powers get really close to integers?
Are we questioning if that's like a
Yeah,
surefire way
exactly.
to identify a Piso number?
Precisely.
Could there be like imposters out there?
That's the question.
Okay.
So, we know that Piso numbers have this property,
Right.
but can we prove that any number that has this property must be a Piso number?
So we're trying to figure out
Yeah.
if that's like a unique characteristic.
Exactly.
Yeah.
And the current proof that we have, that links this behavior to Piso numbers,
Mm-hmm.
relies on the assumption that the number is algebraic.
Okay.
So the Piso-Vijar-Yargovann problem asks,
Yeah.
what if we don't know that beforehand?
Okay.
Can we still prove that it must be a Piso number just because its powers get really close to integers?
So it's like we're detectives trying to figure out
Yeah.
if this one clue
Right.
is enough to solve the case.
Exactly.
That's a fascinating problem.
And it's a very deep question.
Yeah, it really shows you how much
Yeah.
we still don't know
Exactly. There's so much more to explore.
about these
And
special numbers.
It really pushes the boundaries of our understanding.
It really is amazing how much depth there is to this
Yeah.
idea of almost integers.
It is.
It makes you wonder what other mathematical secrets are still out there waiting to be discovered.
Right?
But before we wrap up,
Yeah.
I'm curious about those other sets of numbers you mentioned. Like Salem numbers.
Yes.
You said they were related to Piso numbers.
They are.
That's-
So Salem numbers are indeed closely related to Piso numbers.
Okay.
They're kind of like siblings
Huh.
with similar traits but distinct personalities.
Okay.
So both Salem and Piso numbers are real algebraic integers greater than 1. The key difference lies in their conjugates.
Okay.
Remember that all conjugates of a Piso number have absolute values that are strictly less than 1.
Right.
Well, a Salem number has at least one conjugate with an absolute value equal to 1,
Oh.
while all the rest have absolute values less than 1.
So they're They're kind of like pushing the limits
They are.
of that conjugate test that we talked about.
Exactly.
Does this difference in the conjugate affect how they behave
It does.
compared to piso numbers?
So while the powers of piso numbers get extremely close to integers, the powers of Salem numbers exhibit a slightly more complex behavior.
Right.
They don't necessarily converge to integers, but they kind of dance around them.
Oh, interesting.
Staying remarkably close without actually settling down.
So they're kind of like the rebels of the number world.
Yeah.
Are there any like famous Salem numbers?
That's a good question.
Like the golden ratio is a famous piso number.
So unlike piso numbers where we have well-known examples like the golden ratio and the plastic constant, finding specific examples of Salem numbers is a bit more challenging.
Okay.
In fact, we don't even know for sure if there's a smallest Salem number.
Oh, wow.
Mathematicians have discovered various families of Salem numbers.
Okay.
But pinpointing the absolute smallest one remains an open question.
Another mathematical mystery.
It is. It is.
It seems like the more we learn about numbers, the more we realize how much more there is to explore.
That's the beauty of mathematics.
Yeah.
Every discovery opens up these new avenues for exploration, new connections to make, new questions to ponder.
Well, I feel like we've been on quite a mathematical adventure today.
We have.
We've explored this fascinating world of piso numbers.
Yes.
Their unique properties.
It's been a great deep dive.
It has their connection to almost integers.
Right.
And even their surprising appearances in architecture.
Exactly.
We've also touched on the mysteries of Salem numbers. And this intriguing piso Vijayargavan problem.
Yes.
And it's clear that this is just the tip of the iceberg.
Absolutely.
There's a whole universe of mathematical wonders out there.
There is.
What I find so compelling about this whole topic is just how these piso numbers connect seemingly different areas of math.
Exactly.
Like we've got number theory, we've got Diophantine approximation.
What bridges the gap?
And even the aesthetics of architecture.
It's beautiful.
Yeah, it's a beautiful reminder of how connected knowledge really is.
Yes.
And how powerful mathematical exploration can be.
Absolutely.
Well, I hope our listeners feel inspired.
I hope so too.
To continue exploring the world of numbers.
Yeah.
Who knows? Maybe one of you listening will be the one to solve the piso Vijayargavan problem.
Right.
Or discover the smallest Salem number.
It's possible.
Until then.
Yeah.
Happy exploring.
Happy exploring.